Hi everyone, I'm grateful for the opportunity to share our work on developing an interpretable multimodal model to identify biomarkers that can predict drug treatment response in neuropathic pain. Now, why do we want to identify the biomarkers for drug treatment response in neuropathic pain? There are several key motivations. The first one is that neuropathic pain affects around 10% of adults over the age of 30. Current drug treatments often have limited efficacy and poor tolerability. And then there's a lack of reliable biomarkers to predict who will respond to treatment. However, prior research suggests that structural and functional brain alterations may help us stratify patients based on their pain profiles. By identifying robust and interpretable biomarkers, we can move towards personalized treatment strategies tailored to the individual patient and more effective drug development by targeting specific neurological mechanisms involved in neuropathic pain. However, modeling this type of data comes with several key challenges. One of the most significant is intersite heterogeneity, which is inherent in multi-site datasets. This variability is driven by factors such as patient demographics, which includes age, sex, and treatment history. And another is acquisition parameters, particularly differences in MRI protocols, for example, the repetition time. And what makes this even more challenging is that each imaging modality is affected differently by these heterogeneous factors. As a result, building a robust and generalizable multimodal model requires careful handling of this variability to avoid confounding and biased findings. To address these challenges, we developed an interpretable multimodal pipeline to identify reliable biomarkers for treatment response. This work builds upon a previous study by our colleagues published in 2022. Our approach integrates two imaging modalities: resonance state functional MRI, where we extracted the functional connectivity, and structural MRI using morphometric features such as gray matter volume and cortical thickness, extracted from the predefined regions of interest, or ROIs. To mitigate confounding side effects, we experimented with two methods: domain adaptation, which learns a site invariant feature space, and combat, a widely used statistical harmonization technique. More importantly, we use linear models, which provide inherent interpretability, allowing us to pinpoint which brain regions or connections that are most predictive by simply inspecting the model coefficients. We evaluated our model using three datasets: our in-house Sheffield dataset used for cross-validation, a private dataset from Oxford, and a public dataset from OpenNeuro, both used for external validation. These external datasets allows us to test the model under two distinct generalization scenarios. The Oxford dataset shares the same pain profile and treatment as Sheffield's, but differs in scanner parameters. For instance, the repetition time is 2.5 seconds in Sheffield and 1.3 seconds in Oxford. In contrast, the OpenNeuro dataset involves a different pain condition and treatment, yet has similar scanner parameters, allowing us to isolate the impact of pain type. We also evaluated our model on a particularly challenging subset, patients who receive placebo treatments, to assess how well the identified biomarkers generalize across different treatment mechanisms. This figure illustrates the performance of our models, comparing unimodal and multimodal approaches, with and without adjustments for side effects. As shown, our multimodal models can significantly outperform unimodal ones in external validation, demonstrating the value of integrating both functional and structural information. Notably, domain adaptation provides the largest boost in performance on the Oxford dataset, likely because it effectively compensates for scanner-related differences, such as repetition time variability. That said, all models struggle to predict placebo responses, which may indicate that placebo effects are driven by mechanisms not captured by current imaging biomarkers or lie outside the scope of what our models are designed to predict. This figure highlights the ROIs captured by our model based on fMRI features. The biomarkers identified are consistent with previous findings in the literature. In particular, we highlight regions such as the medial prefrontal cortex and the intraparietal sulcus, both of which have been repeatedly linked to pain processing and modulation. We also observed that several biomarkers consistently emerged across cross-validation models, appearing in over 70% of the trained models, This level of consistency reinforces their potential reliability and stability as predictive features. At the network level, we identified discriminative patterns involving the default mode, visual, and salience network, all of which have been previously associated with diabetic neuropathy in the literature. Among the structural features, we identified 4 regions of interest that appeared in over 80% of the cross-validation models, demonstrating strong consistency across folds. Of the structural measurements considered, gray matter volume emerged as the most discriminative features. Overall, these findings highlight the robustness of the identified biomarkers, reinforcing their potential clinical relevance for understanding and predicting treatment response in neuropathic pain. So, to summarize our work, we propose an interpretable multimodal model to predict drug treatment response in neuropathic pain. We demonstrated how multimodality and domain adaptation can significantly improve model performance, especially in the presence of site-related variability. Finally, we identified reliable and biologically meaningful biomarkers consistent with previous literature, reinforcing the interpretability and potential clinical utility of our approach. This marks the end of my presentations. Thank you for your attention.